Good morning, good afternoon, everyone. My name is Michael Creek, Marketing Communications Manager at DSM Engineering Materials. I'll be your moderator for today's webinar on replacing metal with advanced thermoplastics. And before giving the word to the presenter, I'd like to remind you this is a live webinar and we will be hosting a Q&A at the end. So feel free to submit any of your questions through the questions panel available on the right-hand side of your screen, or if you're following us via the app, make sure you click the question mark icon and submit your questions there. I'll now give the floor to Ron Krotwaar. Please go ahead.
Hello, ladies and gentlemen. Welcome to this webinar on metal replacement. My name is Ron Krotwaar. My background is mechanical engineering at the University in Eindhoven. I've been active for DSM since 1999. I started as design engineer, then I did CAE and FEM simulations. After that, I went into application development, and now I'm doing market development for metal replacement. The focus was always on automotive, so I've been active in the field of air management, powertrain, structural parts, and metal replacement. The content of this webinar. First, I would like to highlight some take-home messages. Then I would like to show you the details on why to replace metal with plastics. I'll also go into details on solution directions that we can provide you and which materials to take. I will go into the class-leading portfolio of DSM, and I will show you the support that DSM can deliver in the project. It would be great if you could take the following messages with home. So first of all, plastics can lead to higher part performance, although generally speaking, they have lower mechanical properties. The material choice as such depends on the balance between application environment, long-term performance, and cost requirements. DSM has an extensive portfolio of best-in-class PPA, PPS, and PA46 materials that opens further opportunities for metal replacement. And DSM has years of experience in metal replacement, and we can build on an extensive application knowledge to support you with the best advice to come to a most efficient solution. So, why to replace a metal with plastics? There are many aspects, and the three of the very important aspects are cost reduction, sustainability, and design freedom. Regarding cost reduction, the material costs as such of a plastic can be lower compared to metal, but also because you can save weight in many cases, you could have a lower total cost of ownership of the application and use. So it could save fuel, it could improve the load efficiency, for example, of trucks, and reduce CO2 penalties. And also it can avoid secondary operations in many cases. So for example, a plastic comes out of the tool ready for use, where, for example, a metal could use still milling or coating to come suitable for the application. Regarding sustainability, processing of plastics can use lower energy than metals, and also you might have less waste if you compare it, for example, to metal stamping process. It could lead to 30 or 40% weight reduction, and of course we already mentioned the lower emissions in use if you have a lower weight part in a vehicle, for example. And also the overall lower footprint in case you are using plastics that are built from biological building blocks. Regarding the design, the plastic has more design freedom in general than, for example, if you would look to metal stamping, but also even more design freedom than, for example, aluminum die casting. So it brings more complex shapes into feasibility. And also the plastic as such has a different damping performance, so higher damping, intrinsic material damping than a metal. So also this could lead to a shift in natural frequencies in your application, to noise reduction and an improved comfort and feel. So which solution directions are there? I'm highlighting 3 here. So you can look at multi-material solutions in case a full plastic solution would not be working. That could, for example, be the case if the loads are so high and the design space is so limited that a plastic cannot be used. In that case, you can work with a combination of metal and plastic together. So in that case, you would use the metal for the high load carrying area, and you would, for example, use the plastic for the integration and the design freedom, for example. Composites. Composites is also something that the DSM is offering. So we have at ATC, we call it, Advanced Thermoplastic Composites. That's UD tape with glass or carbon fiber. And it can be used for winding or tape placement in tools, or you can make woven structures or plaques with that. And the strong point of this is, of course, that you're free to choose the orientation of the fibers, and you can really take the best out of the material performance that you need for your application. I will not go into further details on this section, but you can, for example, sign up for the Advanced Materials Forum of DSM, which will take place on 23rd of April, and then there will be a session where this is explained in details. And of course, the full plastic solutions, which is actually the focus of this webinar, and I will go into the details on that in the following sheets. So the plastic is especially suitable for complex and highly machined shapes. So the pictures that you see here already show that you have complex parts with a lot of ribbing. It opens up design freedom here. At the left bottom side, you see a multi-material solution that DSM provided from an oil sump. And in the center picture in the bottom, you see a aluminum part which has some machined areas, so contacting areas with surrounding parts that are using secondary operations. So that will, of course, boost the costs of the aluminum part. And by replacing this type of parts, our experience is that we can come to 40% lower weight and around 30% lower cost. That leaves us, of course, to the question, what is the right material to use? What you see here is the pyramid of amorphous and semi-crystalline materials. And the materials that are here colored in a box, these are within the portfolio of DSM. So what pops into the eye basically is that DSM has materials throughout the whole pyramid from bottom to top. And then, of course, the question is which material to use, because there are many factors playing a role when choosing the right material. And you can see here, for example, there are environmental factors, performance plays a role, design, processing that is important. And as a matter of fact, this is something in which we would like to search the discussion with you as our customer to see which of these properties are important, and then together come to the right material choice. And DSM already has a very long and broad track record in automotive, here for metal replacement. So you can see here at the left side, you can see applications that have been converted from metal into stanel. In the center section, you see Aquilon with paddle brackets, with air intake manifolds, airbag containers, Arnott and Xytron, specifically materials with very good dimensional tolerances. You can see here, for example, throttle valve actuators, wiper actuators, and also at the right side, our PPA material, Forti or Forti Ace, which is used for applications that see a lot of heat and still need very good dimensional properties and high stiffness and strength at this temperature field. So typical applications, heat shields, clutch slave cylinders, and structural engine covers in this case. But with the materials that we have now in our portfolio, we can also open up the room for more challenging applications. And I've highlighted here several structural parts in a vehicle, and I've also made a small selection between green and blue. Green, I would say, is typically suitable for use with plastics. Blue would be materials, would be applications in which you could use plastic materials that are below engineering plastic level of DSM, for example, so not in the polyamide range, and other ones, for example, bumper beams, crash boxes, fender modules. These typically are applications that need extremely high energy absorption during crash, for example, and these are a little bit far-fetched. So typically applications here like transmission housings, mounting brackets, housings for e-components. These are typically applications that can be converted from metal into plastic with our new portfolio. What you can see here and also in the next slides is I want to show you that we are pushing the boundaries. So we are pushing the limits to further for metal replacement. And I'm always highlighting here one of the important properties that you need in case you want to convert the metal into plastic. So one of the things which is familiar for a metal is, of course, the linear performance profile over the whole temperature range of the application. And what you can see here is a Forti Ace, what I've highlighted. The Forti Ace at the left upper side, you can see the glass transition temperature. It's 160 degrees Celsius. And at the right side, you can see the DMTA curve showing that actually it has a very stable stiffness and strength over the whole temperature range within a vehicle up to, for example, 150, 160 degrees, which is typically the maximum for structural parts. Another important point for automotive environment is chemical exposure, so resistance against chemicals that might occur. So in an automotive environment, you will find salt spray, you will find water glycol, transmission oils, all kinds of liquids. And right here, I also would like to highlight two of our grades. So one is also the Forti Ace. You can see that in the left upper picture, we have done 1,000 hours of exposure in acid, so sulfuric acid. And you can see that after 1,000 hours, it still has 87% of the properties left. And you can see next to it the peak material, which of course still has 100% of properties, but is also in a completely different price range than our Forti. And also here it opens up new possibilities to replace metal with a commercial interesting proposal, for example. In the center section, you can see the transmission oil resistance of Forti Ace. So also here you can see that the curves are still at a very high level, very good retention, even up to 3,000 hours. And at the right picture, you can see our Xitron PPS. So I've shown three curves. The bottom one is a competitor curve. Then the yellow one is our G4024T, which is a 40% glass fiber PPS. And the upper curve is actually our specifically water glycol stabilized grade called G4080HR. And we're talking here about 10,000 hours exposure at 135 degrees. So it's very suitable material for use in thermal management modules and other cooling applications that see this type of long exposures. Then, of course, I mean, you have a high temperature conditioned environment within automotive. So actually, it's not the case that if you have an application which is exposed to 150 degrees Celsius, that the material that you're looking at will automatically be dry. what you can see at the left upper picture is our ranking basically of fatigue performance versus the dry modulus. At 120 to 150 degrees Celsius. So you can see here that, for example, the Forti is the absolute best material that we can provide you with. But if you would look, for example, at a conditioned environment that might occur because a material is generally in a vehicle more at 23 degrees Celsius and 50% relative humidity than it is exposed to the actual high temperature. So over lifetime, you can see that in the right upper picture, it might balance itself into an equilibrium solution where it's approaching conditioned properties. And in that case, you have to look at conditioned properties of the material at 120 to 150 degrees Celsius. And in that case, our Stanel is the absolute best performer in this type of environment. Also, regarding fatigue performance, you can see here how our Stanel and Forti Ace, are performing versus competitor PPAs. So you can see the Stanel TW241F10, which is shown in the cyan curve, and the Forti Ace MX53 is the green curve. And you can already see that we have a very good retention of properties even after 1 million cycles at high stress levels. So fatigue is typically something that you can see in cyclic loaded structural parts, which are heavily loaded in the construction of the body in white itself, for example. Then Weldline strength, it's also a very important point. You can see at the right side of this screen, you can see an exaggerated picture of a Weldline. Of course, this is not a real Weldline, how you would normally like to see it in a part, but this is a short shot. But it actually shows very nicely how flow fronts are colliding and a connection needs to be built from one flow front to the other. And typically these weld lines are in areas that you cannot always control. And these are the weakest points in a construction in many situations. So if you look, for example, at bolt holes, you might have weld lines behind bolt holes that you cannot really influence. So it's really at the end of flow. And then you're very dependent on what the material performance can bring. In this situation, I would like to highlight specifically our Stanel. You can see here at the left picture, or at the left table, you can see multiple materials being mentioned, and Stanel has as such not the highest weld line performance of what we can offer, but it's one material that can reach this theoretical weld line the most easy in practical situations. So if you look at PPA materials, not only DSM's materials, but in general PPA, also PPS, these are materials which are very sensitive to air inclusions on weld lines, on flow front temperature, on holding pressure. And here, as a matter of fact, the Stanel is more forgiving than the other grades, bringing the weld line performance to a higher level in the application. Creep resistance is also very important, of course. If you have parts that are continuously loaded under all circumstances over the lifetime of a vehicle, for example, you would like to have the part still the same shape at the end of life as the moment that you start. But what I would specifically like to highlight here is the possibility with Forti Ace to eliminate torque limiters, so compression limiters. In many cases, it might be sufficient to use plain Forti Ace without any spacers in bolt holes, because the retention, the creep performance of Forti Ace is at such a high level that over lifetime it is still able to maintain the high tightening or the actual forces in balls, for example, and you can then eliminate those spacers, which is an immediate saving of weight and saving of cost. At the right side of this sheet, you can see it highlighted in a graph. So you can see how a BA66, for example, even with 50% glass, is reducing its actual forces in the bolt due to its creep behavior. And with the Forti Ace, the MX53, you can see that it stabilizes at a very useful and practical high actual force level, and that brings this in many cases into the feasibility to reuse these compression levels. Then, when looking at connected drive and new energy mobility, there is also still a lot of metal being used, and typical requirements here are thermal conductivity, electrical insulation, or electrical conductivity, depending on the application. And often we see that electromagnetic shielding is important. And for this, DSM has a quite broad portfolio on thermal or electrical conductive materials. So you can see here we have materials with high thermal conductivity. We have materials with limited thermal conductivity, but still a very high mechanical performance. And in all options, we also have electrical insulative, but also electrical conductive grades. So there are grades here in the range of Stanel, Xytron, Arnite, and Aquilon. And regarding EMI shielding, also here we have several options to provide you with. At the left side, you can see a metallic enclosure. A metal is very good electrical conductive, and hence also already providing intrinsic shielding performance. And with the plastic, this is not the case. Normal plastic you cannot use for shielding. So the solutions that we provide here are the use of conductive coating, and we did many tests with these types of coatings, so we know what kind of thickness would be needed and what kind of coating we would advise. But also you could use the conductive plastics that I just showed on the previous sheet, and also then you are able to reach higher EMI shielding values, and you can work with carbon fiber composites. Because in that case, the carbon fibers are continuous throughout the part surface, and of course, continuous fibers also provide good conductivity. But in the end, it boils down to a combination of material properties, to EMI physics, and to the design. And actually, also in this design, we can support you because we have the possibility in-house to simulate with CAE how a material and design combination is performing in EMI shielding. The last point that I wanted to mention is the support that DSM can provide during the project. So we have a Plastics Finder online. Plastics Finder is a material database in which you can find all material data sheets, safety data sheets, and processing settings, and everything you need. And you can also directly link to the technical experts in case you have a question. And we have a profound knowledge of materials, how to design, and we also know how to process our materials. We are familiar with the applications and with the market trends, and also tuning our portfolio based on what we see in the market. And we have a very modern building in Geleen in which all the disciplines are combined. So we have people from chemistry, we have the CAE department, we have a lot of application expertise, and even the possibility to make prototyping. So this brings me to the end of this presentation. I would like to highlight the take-home messages again. So I've shown you that we have higher part performance with plastics than with metals in many cases, although the mechanical properties are lower as such. The material choice depends on balancing the application environment, long-term performance and cost requirements. I've shown you our portfolio with class-leading PPA, PPS and PA46. And I've explained you a bit on the expertise that we have and how we can support you. So this brings me to the end. Thanks for listening, and I hope it was interesting. And I think that the moderator now will open the lines for question and answer.
Yes, indeed. Thank you very much, Ron. We'll now indeed be opening up for questions. As a reminder, you can submit your questions by checking the chat panel on the right-hand side of your screen. Type in your question and hit the submit button. There's one question here about price. When would a metal part be cheaper than a plastic part?
When a metal part would be cheaper than a plastic part. Okay, well, that is dependent on the complexity of the part. And it is also dependent on how many parts you need to make. So with, for example, aluminum die casting, the tools would be lasting for about 100,000 or 150,000 shots. With a plastic, you might be able to make way above 1 million parts with one tool. So if you stay within this one tool life, you already have good chances for the metal to be commercially more feasible. But if you go over that, then of course you have to amortize more tools within the production than you have to do with plastics. On the other hand, you have, of course, the secondary operations that I mentioned. So if you have a part which is almost not post-processed with milling or machining, then, of course, also the metal part might be cheaper than a plastic part.
Yeah. Okay, thank you very much. Next question, Alex, thank you for your presentation. Is it possible to share any cost range of the materials you have proposed, substitutes for metal?
Well, that can be shared, but I would prefer not to do that here in this webinar. I would propose that we come back to that after this session online, or we simply have a phone call after that, and we explain the ranges.
Okay. Next question, what would design-wise or assembly-wise be needed to replace metal spacers with Forti Ace?
Yeah, that also is, of course, dependent on the application requirements. But typically what you have to try to achieve is that you get compensated for any creep that might occur in the plastic. So when I say compensation, I mean that you could use a slightly larger bolt head. You could use a lower tightening torque, because the tightening torque that normally is prescribed by OEMs or tiers is based on metal-to-metal contact. And for the application to be functional, you don't need this type of high torque levels. You might want to think about aluminum screws, because aluminum has a little bit more elongation at the same force level than steel, and in that case, of course, compensates easier for any creep that occurs. And you can work with a larger grip length. But these are all tricks that you don't always need to make it feasible. It can also be the case that your application is already fully feasible with simply replacing the metal spacer by a full Forti Ace solution.
Okay, thank you. Yeah, specific question about which material can be used for planetary gear, where my sun gear is PA46.
Where my sun gear?
My sun gear, yeah,
oh,
so planetary
yeah,
gear.
Okay. Yes. Well, gears is not specifically in my expertise area. I know my colleagues are working with gears for already many years. but as far as I know, there are several types of stanel unreinforced material which have very good friction behavior, very low wear. For example, called TW341 or TW441 materials. You could use that as a surface on a gear, and then, for example, use a highly filled stanel as the carrying structure at the inside. But planetary gears is not really in my field of expertise, so we come back to that later.
Okay, good. Next question, are the characterization of the raw materials available to be shared in order to let us carry out simulations?
Yes, so from most of our materials, we have all the material data sets available that you need to create a material data card for the simulation. These can already partially be found in Plastics Finder, and you can also download in Plastics Finder the Excel data. So really the numbers that you can copy and paste into your simulation program if you need. But we also have, of course, our simulation department who is happy to help to convert these numbers into your data sets.
Okay, thank you. No more questions. So as we've also reached the time limit of this webinar, I think it's a good moment to say goodbye and to thank everyone for joining. Don't forget to sign up for one of the other webinars we're also organizing in the coming days. You'll find a link to those webinars in a follow-up email. Next to that, I'd also like to highlight our one-day virtual forum we're hosting on April 23rd. You can choose over 19 different sessions. It's completely free to join, and yeah, you also you find a registration link in the email that will be sent to you. Okay, then thank you very much for joining, and Ron, for your presentation.
Thank you. You're welcome.
And hope to see you soon in an upcoming webinar. Thank you very much.
Goodbye.